The Clean Code Compass, Navigating Software Development for Maintainability and Efficiency. Chapter 1, The Code We Live By, Why Clean Code Matters. Imagine stepping into a bustling city. If its roads are chaotic, buildings are crumbling, and public services are unpredictable, navigating daily life becomes a struggle. Every journey is fraught with delays, unexpected detours, and frustrating inefficiencies. Communication breaks down and resources are wasted. Now, picture a city with well-planned infrastructure, clear roads, sturdy buildings, and reliable services. Life flows smoothly. Inhabitants know where they are, where they're going, and how to get things done. Software, at its core, is no different. It's the infrastructure of our digital world. Just as a well-designed city allows its inhabitants to thrive, well-designed software, what we call clean code, enables developers, businesses, and users to succeed. It's not just about code that works. It's about code that works well, is understandable, and is pleasant to work with. It's a human-centric approach to building technology. What is clean code? At its simplest, clean code is software that is easy to read, understand, modify, and test. While some might view it as an aesthetic luxury, it is, in fact, a crucial investment in the long-term health and success of any software project. Here are the key characteristics that define clean code. Readability. It can be instantly understood by another developer, even months or years after it was written, without needing extensive explanation. Clarity. Its purpose is obvious. There are no hidden assumptions or obscure logic segments. Maintainability. Fixing bugs or adding new features is straightforward, with minimal risk of unintended side effects in other parts of the system. Extensibility. The software can adapt gracefully to future changes and new requirements without requiring a complete rewrite. Testability. It's easy to verify its correctness through automated tests, ensuring reliability and robustness. Simplicity. It achieves its goals with the fewest possible moving parts and the most straightforward logic, without sacrificing functionality. This isn't merely about following a set of rules, it's a mindset. It's a continuous process, a discipline, and an evolving professional ethic. It embodies the spirit of craftsmanship, where careful attention to detail and a commitment to quality are paramount. The cost of dirty code. The opposite of clean code is what we term dirty code or legacy code, often used synonymously with code that is difficult to work with. While it might function initially, its poor design introduces what is known as technical debt. This term, borrowed from finance, is a powerful metaphor. Just as a financial loan incurs interest, technical debt incurs additional future costs due to the expedient, less-than-ideal solutions chosen in the past. Think of it like building a house without a proper foundation or blueprint to save time. You get a house, but it's unstable. Fixing issues or adding new rooms becomes disproportionately expensive and risky. Causes of technical debt. Hasty development, rushing to meet deadlines by taking shortcuts. Lack of standards, no agreed-upon coding conventions or quality gates. Inexperienced teams, developers unfamiliar with best practices. Changing requirements. Poorly managed shifts in project goals that lead to quick, messy patches. Consequences on projects and teams. Slowed development, every change becomes a struggle. Developers spend more time deciphering existing code than writing new features. A simple bug fix might require hours of tracing obscure logic, leading to missed deadlines. Increased bugs, complexity breeds errors. The harder it is to understand the code, the easier it is to introduce new bugs, leading to higher quality assurance costs and system unreliability. Developer frustration and burnout. Working with messy, confusing code is inherently demotivating. Developers feel less productive, spend more time fighting the system than building it, and often experience higher rates of burnout and turnover. Business risks. Unreliable software directly impacts the business. Missed opportunities, reputational damage due to poor performance, and the inability to quickly adapt to market changes are all direct results of a codebase burdened by technical debt. Stagnation. The burden of technical debt can become so heavy that a team can no longer innovate. All resources are consumed by maintenance, preventing the business from evolving or delivering new value. The benefits of clean code. Investing in clean code yields significant returns across every facet of software development and its impact on the business. Enhanced productivity. When code is easy to understand and modify, developers can build features faster, fix bugs more quickly, and spend less time on tedious debugging, leading to a noticeable acceleration in delivery. Reduced costs. Lower maintenance overhead, fewer operational issues, and less time spent on debugging translate directly into tangible cost savings over the software's lifetime. Improved software quality. Clear, well-structured code is inherently more reliable, stable, and performant. This leads to a better user experience and contributes to the business's reputation. Better collaboration. Teams work more effectively when everyone can understand and contribute to each other's code. This fosters a shared sense of ownership and accelerates knowledge transfer. Easier onboarding. New team members can ramp up faster, contributing meaningfully sooner. The learning curve is significantly reduced when the code base welcomes them with clarity rather than presenting a labyrinth of confusion. Greater developer satisfaction. Working with clean code is more enjoyable and fulfilling. Developers feel more in control, more productive, and less frustrated, leading to higher morale and better team retention. Sustainable growth. Clean code allows software to evolve gracefully. As business needs change, the system can adapt without breaking, ensuring the technology supports the long-term strategic goals. True efficiency. While a clean, well-designed solution might take a little longer to build initially, it is truly efficient over its entire lifespan. It makes future profiling and targeted optimizations far easier, reducing total cost of ownership and ensuring optimal performance where it truly matters. Clean code as a professional ethic. Embracing clean code is more than just adopting a set of technical practices. It's about professionalism. It acknowledges that software development is a craft, and like any craft, it demands skill, care, and a commitment to quality. One powerful metaphor that encapsulates this ethic is the Boy Scout rule: always leave the campground cleaner than you found it. In software, this means that whenever you touch a module, a function, or a file, you should strive to leave it in a slightly better state than you found it. Even minor improvements, accumulated over time, can transform a chaotic code base into a well-ordered one. It signifies a personal responsibility for the quality of one's output and a genuine care for the long-term health of the project and the well-being of future developers, including your future self. A roadmap for the book. This book is your compass to navigating the often complex world of software development with confidence and skill. We'll start at the foundational level, exploring the critical role of meaningful names in speaking clearly through your code. From there, we'll dive into crafting functions that do one thing and do it well before moving to the truth behind strategic commenting and documentation. We'll then tackle how to build robust systems by designing clean classes and objects, and how to ensure your software is resilient by mastering error management. We'll cover how clean code facilitates effective testing and delve into the fundamental principles of software design that guide larger architectural decisions. Near the end of our journey, we'll explore the relationship between clean code and performance, revealing how true efficiency is achieved. We'll then discuss the continuous process of refactoring to keep your code base pristine, and how to foster collaborative craftsmanship within a team. Finally, we'll reflect on the unending journey of mastering your craft, recognizing that learning and refinement are lifelong endeavors for any software professional. Summary key takeaways. Clean code is not an optional extra. It's a fundamental investment in the long-term success of any software project. It's about writing code that is easy for humans to understand, modify, and maintain, recognizing that code is read far more often than it is written. The hidden costs of dirty code, technical debt, can cripple development speed, increase bugs, burn out teams, and ultimately undermine business goals. Conversely, embracing clean code leads to enhanced productivity, reduced costs, superior software quality, improved collaboration, and increased developer satisfaction. Approaching clean code as a professional ethic means taking personal responsibility for the quality of your output and continuously striving to leave the code base better than you found it. With this foundation, let's begin our journey by exploring the very first building block of readable software: effective naming. Chapter 2: Speaking Clearly, the Art of Meaningful Names. Imagine trying to read a story where the main character is simply called Person A, the villain Person B, and the mysterious object that drives the plot is just Thing. How quickly would you lose interest? How difficult would it be to follow the narrative, understand the motivations, or grasp the stakes? You'd constantly pause, trying to deduce context, perhaps even having to reread previous sections just to keep up. Now, apply that to code. In programming, names are not merely labels, they are the fundamental narrative elements. They are how we communicate our intentions, our design choices, and the very purpose of our software to other developers and to our future selves. If your variables are named X or temp, your functions do something or process data, and your classes manager or utility, you're forcing your readers to constantly deduce, guess, and reread. This is why the art of naming is not just a stylistic preference, it's the bedrock of readable and maintainable code. The importance of good naming. Good names are the primary source of truth in your code, more so than comments. They tell a story about the software and its components. Clarity. A well-chosen name instantly reveals its purpose and leaves no room for ambiguity. Self-documentation. When names are clear, the code explains itself. This significantly reduces the need for comments, making the code cleaner and less prone to outdated explanations. Reduced bugs. Misunderstood names lead to incorrect assumptions about how components work, which inevitably leads to logical errors and bugs. Faster development. Developers spend less time deciphering ambiguous code and more time building new features or fixing problems. Easier refactoring. When components are clearly named, understanding their responsibilities and reorganizing them safely becomes much simpler. Principles of naming. Good names don't happen by accident. They are the result of thoughtful consideration and adherence to several key principles. 1. Intention revelation. Explain why, not just what. A name should clearly convey its purpose or intent, not just its type or superficial meaning. Consider this common scenario. You see a variable named d. What is d? Days, distance, delta, data. Contrast that with elapsed time in days. The second name immediately tells you why that variable exists and what kind of information it holds. Similarly, a function named process data is vague. What kind of data? How is it processed? If it's a function that calculates an online order's shipping cost, calculate shipping cost is specific and reveals its intent. For classes, user is acceptable, but if your system has different types of users, customer account or employee record would be more meaningful within its specific context. Anecdote: a development team inherited an older system with a variable simply named HP. One developer, used to gaming, assumed health points. Another, working on a power system, thought horsepower. A third, dealing with website metrics, guessed home page views. It turned out to be hours per person for a budget allocation report. The team wasted hours trying to debug issues related to this variable until its true meaning was uncovered. This confusion and the associated rework could have been entirely avoided with a name like hours per person allocated. 2. Avoiding disinformation. Don't mislead. Your names should never mislead the reader. If a variable holds a single customer object, don't name it customer list or customer group. That suggests it's a collection, which, if false, creates immediate confusion and potential for error. Similarly, if you are using list in a name like product list, ensure that the underlying data structure is indeed a list or behaves conceptually like one. If it's a unique set of items, product set, or unique products would be more accurate. 3. Context is king. The meaning of a name is often derived from its surroundings. A variable simply named address might be ambiguous, but within a user profile, shipping address or billing address clarifies its specific role. Inside a product class, price is perfectly clear. However, if that variable were outside the product class, simply named price in a general reporting module, it might need to be product price to avoid ambiguity with shipping price or service price. A function named getTemperature inside a weather station class makes perfect sense. No one expects it to return the current humidity, but in a more generic sensor class, Current reading might be more appropriate if the sensor can detect various phenomena. 4. Consistency. Speak the same language. Once you establish a vocabulary for your codebase, stick to it. If you use fetch to retrieve data from a database, don't arbitrarily switch to get or retrieve for similar operations elsewhere. Consistency within your naming conventions reduces cognitive load for developers working on the extensive codebase. This also extends to adhering to established project, company, or language-specific conventions. For instance, in many programming languages, Boolean variables often start with is or has, e.g., is valid, has permission. Following these shared norms makes your code immediately more readable to anyone familiar with the convention. Examples for variables, functions, classes, and files described. Let's illustrate these principles with examples, focusing on the concepts rather than precise code syntax. Variables, bad, int t equals 5. What is t? Good, hey. Int retry count equals 5, clearly indicates its purpose. Bad, list data, what kind of data? Good, list customer active customers, specific and intentional. Functions methods, bad, do work, too generic. Good, hey. Calculate order total, specific action. Bad, handle input, what input, how handled. Good, validate user credentials, clear action and subject. Tip, functions should generally be named with verbs or verb phrases that describe the action they perform. Classes objects, bad, MGR, abbreviation vague. Good, configuration manager, clear responsibility. Bad, util, too generic, often a sign of a junk drawer class. Good, input validation service. Clear responsibility. Tip, classes are typically named with nouns or noun phrases representing a concept, entity, or service. Files modules, bad, helpers.js, what kind of helpers? Good, user service.js. House is logic related to users. Bad, stuffpy, meaningless. Good, product repository py, manages product data access. Tip, name files after their primary responsibility or the main entity they represent. Pitfalls to avoid. As important as good naming practices are, knowing what to avoid is equally crucial. Abbreviations. Resist the urge to shorten names like mngr, manager, or CFG configuration. Spell them out. The slight convenience in typing is vastly outweighed by the reduction in readability. Single letters, mostly. While I is universally understood as a loop counter in a very short, localized loop, avoid using single letters for variables with any broader scope or longer lifespan. Customer index is far clearer than I if the loop body is several lines long or complex. Meaningless words, words like data, info, item, or value without further context convey almost no information. Customer info is only marginally better than customer. Instead, specify customer profile, order details, shopping cart item. Punny names or jargon, code needs to be universally understood by your team, not just by you. Avoid inside jokes, clever puns, or highly specialized acronyms that are not common knowledge within your domain or team. Encoding implementation details. While sometimes necessary, avoid including extraneous details about the underlying data structure in the name if it doesn't add conceptual clarity. For instance, if you have a variable holding a list of customers, customers is usually sufficient. Naming it customer array list might be unnecessary detail, as the name should describe the concept customers, not the specific container type. Naming in different contexts. The strictness of your naming practices can vary subtly with context. Variables with broad scope, those used over many lines, or those that have a long lifespan in the program's execution, should have extremely descriptive names. Conversely, a very short, temporary variable whose purpose is painfully obvious within a small, contained block of code, like some in a two-line function that adds numbers, can be less verbose. The critical test is, can a new developer understand its meaning immediately without scrolling or searching for other references? Summary key takeaways. Names are your code's primary form of documentation. If your code needs extensive comments to be understood, your names are likely failing you. Prioritize intention. A name should tell why something exists, not just what it is. Avoid ambiguity and misinformation. Ensure names accurately reflect their contents and purpose, never misleading the reader. Be consistent. use a common vocabulary across your entire codebase for similar concepts and actions. Spend time on naming. It might feel like a minor detail, but choosing good names is one of the most impactful investments you can make in the clarity, maintainability, and long-term success of your software. Now that we understand how to speak clearly through our names, let's explore how to organize our logic into manageable, well-defined units. Functions. Chapter 3, Crafting Clarity. Functions that do one thing well. Consider a well-equipped workshop. You wouldn't expect a single tool to hammer nails, saw wood, and tighten screws all at once. Instead, you'd find a collection of specialized tools: a hammer for pounding, a saw for cutting, and a screwdriver for fastening. Each tool does one thing, and it does that one thing exceptionally well. In software, a function, often called a method, subroutine, or procedure depending on the programming context, is precisely like one of these specialized tools. It's a named block of code designed to perform a specific task. The principle here is identical. A function should have a single, well-defined purpose. When functions are small, focused, and dedicated, they become easier to understand, easier to test, and significantly easier to reuse, making your entire code base more robust and flexible. The single responsibility principle, applying it to functions. The concept that a function should have a single, clear purpose is directly derived from a fundamental software design guideline known as the Single Responsibility Principle, or SRP. Applied to functions, it means that a function should have one and only one reason to change. Let's illustrate this with an example. Imagine a function named processOrder. On the surface, this sounds reasonable. But if this function's internal logic looks something like this, described, without specific code: validate the customer's input data for the order. Save the order details to the database. Send a confirmation email to the customer. Update the product inventory to reflect the items ordered. This single processOrder function is doing too much. It has at least 4 distinct reasons to change. If the validation rules for customer input change, this function needs modification. If the database schema for orders changes, it needs modification. If the format or content of the confirmation email changes, it needs modification. If the method for updating inventory changes, it also needs modification. This makes the function fragile and complex. A change in one area might inadvertently affect another. The clean code approach would be to break this down into smaller, focused functions, each with a single responsibility. Validate order input. Save order to database. Send order confirmation email. Update product inventory. Now, if the email format changes, you only modify send order confirmation email, confident that you won't accidentally affect order validation or inventory updates. This separation of concerns makes the code significantly more manageable and less prone to errors. Function size and structure. Clean functions tend to be small. While there's no magic number of lines, the key is that a function should be comprehensible at a glance, without needing to scroll or spend more than a few seconds understanding its purpose and logic. Smallness. Most experts agree that functions should rarely exceed a handful of lines, often staying under 20 to 30 lines. If a function grows larger, it's usually a strong indicator that it's doing too much and can be broken down further. Deep versus wide. Think of a function call hierarchy. Clean code tends to be deep, meaning functions call other, smaller, more specific functions. This creates layers of abstraction. Conversely, a wide function tries to accomplish many peer-level operations directly within itself, leading to long, flat, hard-to-read code blocks. Limited indentation. Excessive nesting of conditional statements, if-else, or loops makes code difficult to follow, often leading to the arrowhead anti-pattern, where your code's visual structure looks like a pointy arrow. If you see more than 1 or 2 levels of indentation, it's a strong hint that the inner block of code performs a coherent subtask and could be extracted into its own separate function. This improves clarity by providing a descriptive name for that block of logic and reduces the complexity of the calling function. Arguments. Fewer is better. When designing functions, the number of arguments, the inputs passed to the function, is a crucial consideration. Ideal. The simplest functions take no arguments, indicating they rely only on their internal state or constants. Preferable. Functions with 1 or 2 arguments are generally easy to understand and use. Acceptable with caution, 3 arguments can be tolerated, but they require careful thought and excellent naming to ensure clarity. Warning sign: more than 3 arguments is often a strong indicator that the function is doing too much. It might be attempting to operate on too many disparate pieces of information, suggesting that those related pieces of information should be grouped into a single object or concept that is passed as a single argument. Problems with too many arguments: hard to understand. It's difficult to remember the order and meaning of many arguments, leading to incorrect usage. Hard to test. Testing becomes complicated as you need to simulate many combinations of inputs. Reduced reusability. Functions with many specific arguments are less generic and harder to reuse in different contexts. Common anti-patterns related to arguments. Side effects. A function should not secretly modify data outside its clear scope or return value. For example, if a function named calculateTotal also surreptitiously saves the total to a database or modifies a global variable, that's a hidden side effect. This violates the single responsibility principle because the function now has 2 concerns: calculating and saving. Side effects make debugging and understanding code incredibly difficult. Flag arguments. Avoid using Boolean parameters, often called flag arguments, that cause a single function to perform different behaviors based on the flag's value. For example, a function createAccount user isAdmin should ideally be replaced by 2 separate, clearly named functions: createUserAccount user and createAdminAccount user. Each of these new functions has a single, unambiguous purpose, leading to cleaner calls and easier understanding. Error handling within functions. How functions deal with errors significantly impacts their cleanliness. The preferred approach in most modern languages is to use exceptions for handling unexpected or error conditions. Preference. Exceptions. When an error occurs, e.g., a file not found, invalid input, database connection failure, the function throws an exception. This approach separates the error handling logic, what to do when things go wrong, from the happy path logic, what to do when things go right. This makes the primary flow of the code much cleaner and easier to read, as you don't have to pepper it with constant error checks. Avoid error codes. Historically, some approaches involve functions returning special error codes, e.g., 0 for success, non-zero for different error types. This forces the calling code to constantly check these codes. If result equals success, handle error. This clutters the code, makes errors easy to miss, and mixes error handling deeply into the main logic, making it harder to follow. Naming functions. Just like variables and classes, functions demand descriptive names. The rule of thumb for function names is to use verbs or verb phrases that clearly describe the action they perform. Good examples: calculateArea, save customer record, delete product, is valid email address, authenticate user. These names immediately tell you what the function does. Avoid generic names like do work, handle stuff, or process items. Be specific: process received items, handle user authentication. When a function modifies an object's state, its name should reflect that side effect, such as update inventory or apply discount. Extracting logic. Refactoring for better functions. One of the most powerful techniques for creating clean functions is extract method, or extract function, extract procedure. This is a primary refactoring technique that you will use constantly. The process: when you review a function and identify a block of code within it that performs a single, coherent subtask, even if it's just a few lines, you move that block into a new, separate function. You then give this new function a clear, descriptive name that explains what that extracted block of code achieves, and replace the original lines of code with a call to your newly created function. Example described. Imagine a long function called prepareAnswerReport. That has a section responsible for gathering data from various sources, another section for formatting the report, and a final section for sending it via email. Instead of all that inside one function, you would extract the data gathering section into a new function named GatherReportData. Extract the formatting section into a new function named FormatReportContent. Now your original prepareAnswerReport, function becomes much shorter and clearer, perhaps looking conceptually like data equals gather report data. Formatted report equals format report content, data. Send report by email, formatted report. Benefits of extracting functions. Improved readability. The larger function now reads like a high-level outline of its steps, making it much easier to grasp its overall purpose. The details are hidden in clearly named subfunctions. Promotes reusability. The extracted function might be useful in other parts of your application, leading to less duplicated code. Simplifies testing. Each small, extracted function can be tested independently, making your test suite more robust and your debugging process faster. Reduces complexity. Breaking a large problem into smaller, manageable chunks makes the overall system less daunting and easier to maintain. It's similar to a complex recipe. Instead of listing every single detail for prepare the sauce within the main recipe steps, you'd simply have a step that says prepare the sauce, and then refer to a separate, dedicated section or subrecipe where all those specific steps are detailed. Summary key takeaways. Functions are your software's specialized tools. They should do one thing and do it well. Adhere to the single responsibility principle. A function should have only one reason to change. Keep functions small, easy to read, and with limited indentation. Break down large functions into smaller, more focused ones. Minimize the number of arguments and avoid problematic flag arguments or hidden side effects. Prefer exceptions for handling errors to keep the main execution path clean and readable. Name functions with strong verbs that clearly describe their actions. Regularly use the extract method, refactoring technique, to split complex logic into coherent, well-named subfunctions. With well-named elements and clearly defined functions, our code begins to speak for itself. But sometimes, code isn't enough, and that's when we look to comments and other documentation. However, as we'll see in the next chapter, even these need to be deployed strategically. Chapter 4. The Truthful Narrative, Strategic Commenting and Documentation. Good code needs no comments. This aphorism, often repeated in programming circles, holds a kernel of truth. It expresses an ideal that your code, through clear naming, as discussed in Chapter 2, and well-structured functions, as explored in Chapter 3, should be so self-explanatory that it requires minimal external explanation. In the perfect world, a piece of clean code would tell its own story, its purpose evident to anyone who reads it. However, the reality of software development is often far from perfect. While the goal remains to write highly readable code, there are legitimate reasons for comments and external documentation. The challenge lies in distinguishing between helpful, strategic comments and those that are redundant, misleading, or simply code, smell, a sign of deeper problems. A comment, unlike code, can lie. It can become outdated, misleading, or simply be noise, making the code harder to trust and maintain. Strategic use is key. The role of comments. Explaining why, not what. The most crucial distinction to grasp about comments is their purpose. Bad comments, explaining what the code does. If your code is clean, it should inherently tell you what it does. Comments that merely reiterate the obvious are redundant. For example, a comment stating, "This increments the counter by 1, followed immediately by a line of code that literally increments a numerical variable by 1, adds no value. The code already tells you what it does. Such comments clutter the codebase, taking up space and forcing the reader to mentally filter them out. Good comments, explaining why a decision was made. The true power of a comment lies in explaining why a particular piece of code exists, why a specific design choice was made, or why a seemingly complex or unintuitive solution was necessary. These comments provide context or intent that the code alone cannot capture. They fill in the gaps that even the cleanest code might leave. Consider this scenario. This workaround is needed because the third-party library has a known bug in version 1.2 that incorrectly generates user IDs. Remove this workaround after upgrading to version 1.3 or higher. The code itself might just show a manipulation of a user ID, but this comment explains the reason for that manipulation, why it's a temporary solution, and when it can be removed. This is invaluable information that the code itself cannot convey. Types of good comments. When used deliberately and strategically, Comments can serve several valuable purposes. Legal comments. These are typically boilerplate comments required for copyright, licensing, or authorship information at the top of files. They are often automatically generated or mandated by organizational policy. Informational comments, providing critical information not easily inferred from the code itself. Explaining complex regular expressions that are notoriously difficult to decipher. Describing specific data encodings or expected formats for external data that deviate from standard conventions. Clarifying the nuances of external system integrations or third-party API quirks. Clarification of intent, when a design decision or a logical shortcut might appear confusing or counterintuitive to a future reader. For instance, we are intentionally negating the result of this function because the external payment gateway API returns true for a successful operation, but our internal system expects false to denote success. The code would simply show the negation, but the comment explains the crucial behavioral discrepancy. Warnings, TODOs, or fix-me's. These are temporary notes to oneself or the team, indicating known issues, areas needing refactoring, or planned future work. They should be accompanied by context and, ideally, a ticket number from your project management system. For example, TODO, refactor this into a separate user authentication service once all identity providers are integrated. JIRADEF 456. These should be used sparingly and actively addressed, lest they become stale. Public API documentation comments. For public classes, functions, or modules designed to be consumed by other developers, whether within your team or external users, well-structured documentation comments are essential. These are typically processed by documentation generation tools, like Javadoc, DocStrings, or JSDoc, to produce official API documentation. They explain the overall purpose, parameters, return values, potential exceptions, and general behavior to those who will use your code, without needing to delve into its internal implementation details. Types of bad comments. Just as there are good comments, there are many types of comments that actively harm a code base. Redundant comments. Comments that simply repeat what the code already clearly states. These are pure noise. Misleading comments. This is arguably the worst kind of comment. A comment that is outdated and no longer accurately reflects the actual code is dangerous. It can send developers down the wrong path, wasting valuable debugging time and potentially introducing new bugs because they trust the comment more than the code. Code evolves, comments often don't. Mandated comments. Policies that require comments on every function, every variable, or every 10 lines of code often lead to superficial, unhelpful comments written merely to satisfy a rule, not to convey meaningful information. Commented out code. Never leave commented out code in your codebase. It clutters the view and suggests indecision. If you think you might need it later, your version control system, like Git, is designed precisely for that. You can always retrieve previous versions of your code. Commented out code causes confusion. Is it debug code? Is it old code? Should it be deleted? Journal comments. Comments providing a historical log of changes within the code itself, e.g., modified by Jane Doe on 2023 to 10 to 26. Added feature X, fixed bug Y. This information is best managed by your version control system, which provides a far more powerful, accurate, and automated history. Noise comments. Any comment that adds no new information or value, simply cluttering the code and making it harder to read the actual logic. This includes closing brace comments, e.g., end, if, or long boilerplate headers for internal-only files. Code as self-documentation. The highest aspiration of clean code is for it to be its own most reliable source of truth. When code is self-documenting, it means that a developer can understand its purpose and behavior simply by reading the code itself, with minimal need to refer to external sources. How do you achieve this ideal? Meaningful names. As discussed in Chapter 2, truly descriptive names for variables, functions, and classes are the most powerful form of documentation. A function named Calculate Customer Loyalty Discount tells you everything you need to know about its purpose without a single comment line. Small, single responsibility functions. As explored in Chapter 3, Functions that do one thing well hide their internal complexity and present a simple, meaningful interface, their name and parameters, to the outside world. Clear class structures, to be discussed later. Well-designed classes and modules organize code logically, making it easy to find and understand related pieces of functionality. Sensible design patterns. Using widely understood architectural and design patterns can convey intent without explicit comments, as developers familiar with the patterns will recognize the structure and its implications. The reflective practice. If you find yourself about to write a comment to explain what a block of code does, pause. Ask yourself, can I refactor this code? Can I rename something? Can I extract this block into a new, smaller, well-named function whose name is the explanation? For instance, instead of a comment like, "This converts temperature from Fahrenheit to Celsius," above a mathematical formula, extract that formula into a new function called convert Fahrenheit to Celsius. The function's name then becomes the documentation, and it is inherently truthful and directly tied to the code's behavior. When external documentation is necessary. While clean code reduces the need for comments, it does not eliminate the need for all documentation. There are specific types of information that are best kept outside the code itself. High-level architecture and design. Diagrams and explanations that describe how different systems, services, or large modules interact, overall data flow, or system boundaries. Code only provides a low-level view. High-level documentation provides the big picture. Complex domain knowledge or business rules. Detailed explanations of industry-specific terminology, intricate business processes, or algorithms that are not immediately obvious from the code. Why a certain calculation is done or what a business term means belongs here. Setup, build, and deployment instructions. How to configure your environment, build the application from source code, or deploy it to a live server. These are operational concerns, not code concerns. External API guides. Comprehensive documentation for external developers consuming your service or library. This includes usage examples, authentication details, and error response specifications. Decision logs. Records of significant architectural or design decisions, including the rationale behind them, alternatives considered, and why certain paths were chosen. This is invaluable for understanding the evolution of the system. Summary key takeaways. Strive for self-documenting code. Use meaningful names, small functions, and clear structures so that the code speaks for itself. Comments should explain why, not what. Use them to clarify intent, explain design choices, or provide context that the code cannot convey. Eliminate bad comments. Ruthlessly remove redundant, misleading, commented out, or noisy comments. Leverage version control. Use tools like Git for tracking code history, not inline journal comments. Complement code with external documentation. Use separate documents for high-level architecture, complex business rules, setup instructions, and external API guides. By being deliberate about how and when we use comments, we ensure that our code base tells a truthful, clear, and easy-to-follow narrative, allowing future developers to understand and evolve the software effectively. Having laid the groundwork with naming, functions, and commenting, our next step is to examine how to structure our code into larger, cohesive units, classes, and objects. Chapter 5. Building blocks. Designing clean classes and objects. Imagine you're organizing a busy household. If every item were scattered randomly, and every chore done haphazardly by anyone, the house would quickly descend into chaos. Now imagine a well-organized home. Kitchen tools are in the kitchen, cleaning supplies in the utility closet, and each family member has clear responsibilities. Everything has its place and purpose, making the household run efficiently. In object-oriented programming, OOP, classes and objects are the primary organizing principles for your code. They help us group related data and the functions that operate on that data into cohesive units, much like designing the specialized rooms and assigning roles in our well-ordered household. Just as a poorly organized home creates clutter and inefficiency, poorly designed classes lead to messy, hard-to-maintain software. Designing clean classes is about creating modular, understandable, and flexible building blocks for your system. What are classes and objects? Before diving into clean design principles, let's briefly define these terms, as they are fundamental to much of modern software development. Class: a blueprint or a template for creating objects. It defines the properties, data attributes, and behaviors, functions, methods that all objects of that type will possess. Think of a blueprint for a car. It specifies the engine, wheels, seats, and how they interact. Object: an instance of a class. It's a concrete entity created from the blueprint. So, a specific Honda Civic parked in your driveway is an object created from the car class blueprint. The goal of designing clean classes is to create objects that are meaningful, encapsulate their internal workings, and interact with other objects in predictable and controlled ways. Clean class design principles. Many principles guide the design of clean classes, often extending the ideas we've already discussed, like the single responsibility principle, to a higher level of abstraction. 1. The single responsibility principle, SRP, for classes. Just as a function should do one thing well, a class should have one, and only one, reason to change. This means a class should encapsulate a single, well-defined concept or responsibility. Bad example described. A class named user that handles, storing users' personal information, name, address, email, managing user authentication, login, password hashing, processing user orders, calculating totals, managing payments. Problem: this user class has multiple reasons to change. If password security standards change, if personal information storage requirements change, or if the order processing logic changes. Such a class becomes a God object or monolith, accumulating many unrelated responsibilities, making it large, complex, and highly prone to bugs when modified. Good example described. Instead, break it down. User profile class stores personal information. Changes only if user profile data changes. User authenticator class service handles login and security. Changes only if authentication mechanisms change. Order processor class service manages order-related logic. Changes only if order processing rules change. Benefit: each class is now focused, smaller, and easier to understand, test, and maintain. Changes to one area are isolated, minimizing ripple effects. 2. Encapsulation, hiding implementation details. Encapsulation is one of the core tenets of OOP. It means bundling data, attributes, and the methods, functions that operate on that data within a single unit, the class, and restricting direct access to some of the object's components. Think of it as a black box. You know what it does, but you don't need to know how it does it. Principle: keep data, attributes, private within the class. Expose only the necessary methods to interact with that data. This protects the internal state of the object and ensures that modifications happen only through controlled, validated methods. Bad example described. A bank account class where the balance is publicly accessible and can be directly set to any value. Problem: account balance equals -100 could be executed directly, leading to an invalid state without any validation or logging. Good example described. A bank account class where balance is private and methods like deposit, amount, and withdraw amount are public. These methods contain logic to validate the amount, e.g., must be positive, and perform necessary updates, e.g., updating transaction history. Benefit: the class controls its own state, ensuring data integrity and enforcing business rules. Changes to the internal representation of the balance, e.g., storing it in a different currency, don't affect external users of the deposit or withdraw methods. 3. Smallness. Keeping classes focused and self-contained. Just like functions, classes should ideally be small. While there's no strict line count, a class should represent a single, coherent concept. If a class has too many attributes or too many methods, it's often a sign that it's violating SRP and should be broken down. Indicators of a too large class. It has many methods that operate on different subsets of its data. It has many if-else or switch case statements that differentiate behavior based on the type or state of an object, suggesting it's trying to manage too many variations. It has methods that are only used by a few other methods within the same class, indicating they might belong in a helper class. For high cohesion, everything in the class belongs together. Cohesion refers to how strongly related, and focus the responsibilities of a single module or class are. A highly cohesive class has members, attributes, and methods that are all related to its central purpose. All its parts work together to achieve a single, well-defined goal. Example described. A customer class should contain methods related to customer data like get contact info, update address, or get purchase history. It should not contain methods like send email notification, which belongs to an email service, or process payment, which belongs to a payment gateway. Benefit: high cohesion makes classes easier to understand, test, reuse, and maintain because all the related logic is in one predictable place. 5. Low coupling. Minimizing dependencies between classes. Coupling refers to the degree to which different classes are dependent on each other. Clean code aims for low coupling, meaning classes should be as independent as possible, communicating through well-defined, stable interfaces. High coupling means a change in one class forces changes in many others, creating a fragile codebase. Strategies for low coupling. Dependency injection. Instead of a class directly creating instances of the objects it depends on, those dependencies are injected, passed into the class, making it easier to swap out implementations or test. Abstraction. Rely on interfaces or abstract classes rather than concrete implementations. For example, a sales report generator shouldn't depend on a specific MySQL database, but rather on a generic database connector interface. Message passing. Objects communicate by sending messages, calling methods on each other, rather than directly accessing each other's internal state. Example described. High coupling. A order processor class directly creates and uses a specific PayPal payment gateway object, making it impossible to switch to another payment method without modifying order processor. Low coupling. Order processor accepts an iPayment gateway interface in its constructor dependency injection. It doesn't care if the concrete implementation is PayPal payment gateway or Stripe payment gateway, as long as it adheres to the iPayment gateway interface. Order processor simply calls payment gateway.processPayment amount. Benefit: allows for greater flexibility, easier testing by mocking or simulating dependencies, and better system evolution. The tell, don't ask principle. This principle is a powerful guideline for designing object interactions. Instead of asking an object for its data and then making decisions based on that data, you should tell the object to perform an action using its own data. This keeps behavior encapsulated with the data it operates on. Bad example described. If customer get balance, order get total. Customer send insufficient funds notification. Here, an external piece of code asks the customer for its balance and then decides what action to take. Good example described. Customer.process order inside customer.process order. If this balance order get total, this send insufficient funds notification. Here, we tell the customer object to process the order. The customer object, knowing its own balance, encapsulates the logic of whether it can fulfill the order and how to handle insufficient funds. Benefit: keeps the behavior close to the data, reduces coupling, and makes classes more intelligent and responsible. Class names, nouns, and noun phrases. As discussed in Chapter 2, class names should be nouns or noun phrases that clearly describe the entity or concept the class represents. Good examples: customer, order, payment gateway, shopping cart, user authentication service, report generator. Avoid generic or ambiguous names like manager, controller, or handler unless they are explicitly qualified, e.g., product manager, order controller. These names often suggest a class that might be doing too many things if not carefully defined. Summary key takeaways. Classes and objects are fundamental building blocks for organizing code, bundling data with the behaviors that operate on it. Adhere to the single responsibility principle for classes. Each class should have one and only one reason to change, representing a single, cohesive concept. Embrace encapsulation. Hide internal implementation details and protect the object's state by exposing only necessary methods for interaction. Strive for high cohesion and low coupling. Ensure that elements within a class are highly related cohesion and that classes minimize their dependencies on each other coupling. Apply the tell, don't ask principle. Tell objects to perform actions rather than asking for their data to make decisions externally. Name classes clearly. Use nouns and noun phrases that accurately reflect the responsibility of the class. Designing clean classes is a continuous process of thought and refinement. By focusing on these principles, you build a robust, flexible, and maintainable object-oriented system that can adapt to changing requirements with grace and efficiency. With our components well-defined, our next step is to ensure that our systems handle the inevitable errors. Chapter 6: Graceful Handling, Mastering Error Management. Imagine a critical infrastructure system, say, an air traffic control system or a hospital's patient management software. What happens when something unexpected occurs? A network connection drops, a disk runs out of space, or a user enters invalid data. If the system simply crashes, freezes, or produces incorrect results, the consequences could be disastrous. Reliable software doesn't just work when everything goes right. It also works predictably and gracefully when things go wrong. Error management is the practice of anticipating, detecting, and responding to exceptional or unwanted conditions within your software. It's not about preventing all errors. Some are external and unavoidable, but about ensuring that your system can handle them without compromising its integrity, user experience, or overall stability. Clean error handling is about making the unhappy path as clear, robust, and understandable as the happy path. The problem with unhandled errors. Unhandled errors are dangerous. They can lead to crashes and instability, a sudden termination of your application, leading to data loss or a complete halt of service. Corrupted data, data being written or read incorrectly, leading to inconsistencies and trust issues. Security vulnerabilities. Error messages sometimes inadvertently expose sensitive system information, e.g., database connection strings, file paths, which attackers can exploit. Poor user experience. Users encountering confusing error messages, unresponsive applications, or losing their work. Debugging nightmares. Without clear error handling, pinpointing the root cause of an issue can be like finding a needle in a haystack. The two faces of error management: errors versus expected conditions. Before diving into techniques, it's important to distinguish between true errors, or exceptions, and expected conditions that are a normal part of business logic. Exceptions, errors. These are truly exceptional and usually unexpected situations that prevent your code from fulfilling its intended purpose in the normal flow. Examples: a network connection failure, a file not found, running out of memory, or an invalid database query. These typically represent a failure that should interrupt the current operation at some level. Expected conditions. These are foreseeable outcomes that are part of the normal operational logic. Examples: a user entering an incorrect password, it's wrong, but the system is designed to handle this. A search yielding no results, or a valid but empty list. These are not errors in the exceptional sense. They are conditions that the code should anticipate and manage as part of its normal operation without throwing an exception. The key is not to use exceptions for everything. Using exceptions for expected conditions can make your code harder to read and debug, as the exception handling mechanism becomes part of the routine flow. Prefer using exceptions. As discussed briefly in Chapter 3, the preferred method for handling true errors in modern programming is using exceptions. How exceptions work conceptually. When a function encounters an exceptional condition it cannot handle internally, it throws an exception. This immediately halts the normal execution flow of that function and propagates the exception up the call stack, seeking a catch block that knows how to handle that particular type of exception. If no catch block is found, the program typically terminates. Benefits of exceptions. Separation of concerns. Exceptions cleanly separate the what to do when things go right, the main logic, from the what to do when things go wrong, the error handling logic. This makes the primary flow of your code much cleaner and easier to read, as it's not littered with if statements checking for error codes after every operation. Robustness. They ensure that errors are not silently ignored. If an exception is thrown, it must be handled at some level, or the program will terminate, alerting you to the problem. Meaningful information. Exceptions carry contextual information, type of error, message, stack trace that is invaluable for debugging and logging. Centralized handling. You can often handle various types of errors in a centralized location rather than duplicating error-checking code everywhere. Pitfalls to avoid with exceptions. Swallowing exceptions. Catching an exception and doing nothing with it, or simply logging it without any further action. This is incredibly dangerous as it hides problems, leading to silent failures that are impossible to diagnose later. Catching generic exceptions. Catching a too broad or generic exception type, e.g., a top-level exception class, without specific handling for different error types. This can hide more specific errors and make it difficult to respond appropriately. Always catch the most specific exception appropriate for your handling logic. Over-reliance for control flow. Using exceptions for expected conditions or as a general-purpose control flow mechanism. This makes code less readable and can be less performant in some environments. Providing context with error messages. When an error occurs, the error message itself is a critical piece of information. Clean error messages are descriptive. They clearly state what went wrong. An error occurred is useless. Failed to connect to the database server at IP address. Connection refused is far more helpful, informative. They provide enough context for a user or developer to understand the problem or take corrective action. Include relevant data points, e.g., the ID of the record that failed to save, the specific file path that couldn't be found. Actionable for users. If possible, guide the user on what to do next. Please check your internet connection and try again, or contact support with error code ABC. Non-revealing for users regarding sensitive info. Be careful not to expose sensitive internal system details, e.g., database credentials, internal server paths, specific library versions, in user-facing error messages. These should be logged for developers, but not displayed to end users for security reasons. The role of logging in error management. Logging is a complementary strategy to exception handling. While exceptions interrupt normal flow, logging provides a persistent record of events, including errors, warnings, and informational messages. Levels of logging. Use different logging levels, e.g., debug, info, warn, error, fatal, to filter the verbosity of your logs. Comprehensive error logs. For every caught exception, log its full details, error type, message, and the complete stack trace. The stack trace is crucial as it shows the entire sequence of function calls that led to the error, helping developers pinpoint the origin. Contextual information. Include relevant context in your logs, such as user IDs, request IDs, timestamps, and any input parameters that led to the error. This makes it much easier to reproduce and debug issues. Avoid overlogging. Don't log trivial details at serious error levels. Flood of logs makes it hard to find true problems. A failed password attempt should be a warning, not a critical error unless it's indicative of a brute force attack. Designing safe APIs with error handling in mind. When designing public APIs, application programming interfaces, or exposing functionality, think about how errors will be communicated to the callers. Fail fast. APIs should fail as early as possible if inputs are invalid or preconditions are not met. Don't proceed with potentially flawed data only to fail much later in the process. Validate inputs at the boundary. Consistent error responses. If your API is external, e.g., a web service, define clear, consistent error structures, e.g., using HTTP status codes for web APIs, specific error codes with descriptive messages in JSON payloads. Documentation. Document the types of errors your API can throw or return, along with their meanings and guidance on how calling applications should handle them. Throw early, catch late principle. This is a guiding principle for optimal exception handling. Throw early. As soon as an error condition is detected, throw an exception. Don't continue processing with invalid data or in an incorrect state. This ensures the error is identified at its source. Catch late. Don't catch an exception unless you can genuinely handle it, resolve the problem, or add meaningful context before rethrowing it. If a low-level function catches an exception but doesn't do anything useful with it, e.g., it just logs it and rethrows a generic error, that's often an anti-pattern. Let the exception propagate up the call stack to a level where there's enough context and capability to perform a meaningful action. E.g., display an error message to the user, roll back a transaction, retry an operation. The practice of graceful degradation. Sometimes, a full recovery from an error is impossible. In these cases, the goal is graceful degradation, allowing the system to continue functioning, perhaps in a reduced capacity, rather than completely failing. Example described. If an external recommendation service is unavailable, instead of crashing, display a message like "Recommendations currently unavailable," and proceed with the core functionality of the e-commerce site. This requires careful design to isolate failing components. Summary key takeaways. Error management is crucial for robust, stable, and user-friendly software. Distinguish between true exceptions, unexpected failures, and expected conditions, handled as part of normal business logic. Prefer exceptions for errors. Use them to separate error handling from normal logic, ensuring problems are not silently ignored. Avoid swallowing generic exceptions. Catch specific exceptions and handle them meaningfully, or let them propagate. Provide rich context with error messages and logs. Be descriptive, informative, and actionable for users, while being mindful of security for internal details. Follow throw early, catch late. Isolate the problem at its source and handle it at a level where meaningful action can be taken. Design APIs with error handling in mind. Validate inputs, fail fast, and provide consistent error responses. Strive for graceful degradation. Allow the system to continue operating, even if some functionality is unavailable, to maintain user experience. Mastering error management is a sign of mature software design. It transforms your code from fragile to resilient, ready to face the inevitable challenges of the real world. Our next step in building clean and reliable software is to ensure its correctness and guard against future regressions, which brings us to the vital role of testing. Chapter 7. The Safety Net. Clean code and unit testing. Imagine a trapeze artist performing without a safety net. Every daring leap becomes terrifying, and a single mistake means catastrophe. Now imagine the same artist, fully confident, knowing that if they miss a catch, a sturdy net will break their fall, allowing them to try again. The net doesn't make them fearless, but it encourages them to push boundaries, knowing they have a dependable backup. In software development, unit tests are that indispensable safety net. They are small, automated tests that verify individual units or components of your code, like a single function or a small class, work precisely as intended. While testing might seem like an extra step, it's not. It's an integral part of writing clean, maintainable, and ultimately, efficient software. Clean code makes testing easier, and comprehensive testing helps keep code clean. Why unit testing matters. Many developers, especially when starting out, might overlook testing or consider it a secondary chore. However, the benefits are profound and directly contribute to the principles of clean code. Confidence in changes. This is paramount. With a robust suite of unit tests, you can refactor existing code, add new features, or fix bugs with confidence, knowing that if you inadvertently break existing functionality, your tests will quickly flag the issue. Without tests, every change is a gamble. Reduced bugs. Unit tests catch defects early in the development cycle, where they are cheapest and easiest to fix. A bug caught before deployment saves significant time, cost, and reputational damage. Improved design. The very act of writing unit tests forces you to think about how your code will be used. This often leads to better modularity, clearer interfaces, and a stronger adherence to principles like single responsibility and low coupling, as discussed in Chapter 5. Code that is hard to test is usually poorly designed. Living documentation. A well-written unit test describes exactly what a piece of code is supposed to do. It serves as a runnable specification, explaining the expected behavior of a function or class in various scenarios. Faster debugging. When a test fails, it immediately points you to the exact function or component that has a problem, significantly reducing debugging time. Facilitates refactoring. As we'll discuss in Chapter 10, refactoring is key to keeping code clean. Unit tests provide the critical safety net that allows you to confidently restructure code without fear of introducing regressions. What is a unit? A unit is the smallest testable part of an application. This typically means a single function or method, a single class. The goal is to isolate the unit as much as possible, testing it independently of other parts of the system. Characteristics of a good unit test. Not all tests are created equal. A good unit test is fast. Unit tests should run in milliseconds. A large suite of fast tests provides immediate feedback to the developer. Slow tests discourage frequent execution. Isolated. Each test should run independently of others and produce the same result regardless of the order they are run or the state of the overall system. This means avoiding shared mutable state between tests. Repeatable. Running the same test multiple times should always yield the same result, assuming the code under test hasn't changed. Self-validating. The test should either pass or fail without human intervention or interpretation. It should not require someone to manually inspect output logs or database entries. Timely. Tests should be written either before the code they test, test-driven development, TDD, or immediately after. Postponing testing makes it less likely to happen and harder to write good tests. How clean code supports testing. The principles of clean code inherently make testing easier. Single responsibility principle. When functions and classes do one thing well, they are naturally easier to test. A function with a single, clear responsibility has fewer variables or conditions to test. Smaller functions are easier to understand and isolate for testing. Low coupling. Code with low coupling is easier to test because you can test individual units without needing to set up complex dependencies. If a class relies on an external service, like a database or an API, you can mock or stub that dependency during testing. A mock is a simulated version of a component that behaves like the real one but is controlled by your test, allowing you to isolate the unit being tested. Clear interfaces. Well-defined interfaces, API of a class or function, make it easier for tests to interact with the code. Absence of hidden side effects. When functions clearly communicate their actions and don't have unexpected side effects, testing becomes straightforward. You can confidently assert that an action will produce a specific outcome without worrying about unintended changes elsewhere. Writing effective unit tests. Conceptual approach. The process of writing a unit test typically involves 3 steps, often called the arrange, act, assert pattern. Arrange, given. Set up the necessary preconditions and inputs for the unit being tested. This might involve creating objects, initializing variables, or setting up mock dependencies. Example. Given a calculator object and 2 numbers, 5 and 3. Act when, execute the actual unit of code you want to test. This is typically a single method call or function invocation. Example. When I call the add method of the calculator object with 5 and 3. Assert then, verify that the outcome of the action is as expected. This involves checking return values, object states, or interactions with mock objects. Example, then the result returned by the add method should be 8. Example test scenarios described, no code block. Let's consider a shopping cart class with an addItem method and a calculate total price method. Test for addItem, arrange, create an empty shopping cart object. Create a product object with a name and price. Act, call shopping cart addItem product quantity. Assert, verify that the shopping cart now contains the product and quantity, and that its item count property has increased correctly. Test for calculate total price. Arrange, create a shopping cart object. Add multiple products with different quantities and prices using addItem. Act, call shopping cart.calculate total price. Assert, verify that the return total matches the expected sum of all item prices and quantities, including any taxes or discounts it's supposed to apply. Edge case test, repeat the above but with an empty shopping cart, asserting the total is 0. Test-driven development, TDD. TDD is a software development approach where tests are written before the code itself. The cycle is: red, write a failing unit test for a new piece of functionality. It fails because the code doesn't exist yet. Green, write just enough production code to make the failing test pass. Don't optimize or add extra features yet. Refactor. Clean up and improve the code base, ensuring all tests continue to pass. TDD can feel counterintuitive at first, but it powerfully drives clean code. It forces you to think about the public interface of your code before you write the implementation, leading to more testable and modular designs. It acts as a continuous design feedback loop. Beyond unit tests, integration and end-to-end tests. While unit tests are foundational, they often don't test how different components interact, integration, or how the entire system behaves from a user's perspective, end-to-end or E2E. Integration tests verify that two or more units, e.g., a service and a database, work correctly together. These are typically slower than unit tests as they involve more complex setups. End-to-end, E2E tests simulate real user scenarios, testing the entire application flow from start to finish, including the user interface. These are the slowest and most fragile, but provide confidence in the entire system. A balanced test suite includes a test pyramid, where you have many fast unit tests at the base, fewer integration tests, and even fewer, slower E2E tests at the top. The bulk of your testing effort should be at the unit test level. Summary key takeaways. Unit tests are the safety net that allows you to confidently make changes to your codebase. They provide immediate feedback, catch bugs early, and act as living documentation. Clean code principles, SRP, low coupling, small functions, directly contribute to code that is easy to test. Conversely, code that's hard to test is likely not clean. A good unit test is fast, isolated, repeatable, self-validating, and timely. Adopt the arrange, act, assert pattern for structuring your tests. Consider test-driven development, TDD, to drive better design and ensure test coverage. While unit tests are paramount, integrate them with integration and end-to-end tests for comprehensive coverage. With a robust test suite in place, you can approach the deeper aspects of software design with confidence, knowing that your foundational components are solid. Our next chapter will delve into these larger-scale design principles that guide the architecture and overall structure of your clean codebase. Chapter 8, Principles of Design, Beyond the Basics. So far, we've focused on the microscopic view of clean code, how to name things, craft functions, manage errors, and test individual units. These are the bricks and mortar. But building a skyscraper requires more than just good bricks. It requires an architectural plan. Similarly, creating robust, maintainable software systems demands an understanding of higher-level design principles. These principles guide how classes interact, how modules are structured, and how the entire system evolves. These design principles often build upon or generalize the concepts we've already discussed, extending them from individual components to the relationships between components. They aim to reduce complexity, enhance flexibility, and make systems easier to understand, extend, and maintain over their lifetime. The solid principles, cornerstones of object-oriented design. The solid principles are a widely recognized set of 5 design principles by Robert C. Martin Uncle Bob that, when applied together, promote the creation of more maintainable, understandable, and flexible object-oriented systems. 1. Single Responsibility Principle, SRP, revisited for greater scope. We've already touched upon SRP for functions, Chapter 3, and classes, Chapter 5. At a higher level, SRP emphasizes that a module, a class, or even a component should have one, and only one, reason to change. Impact on clean code ensures that changes to one part of your system have minimal impact on other unrelated parts. This directly reduces coupling and increases cohesion, contributing to a more stable codebase. If a class has multiple reasons for change, every modification carries the risk of introducing bugs in unrelated functionalities. 2. Open-Closed Principle, OCP. Software entities, classes, modules, functions, etc., should be open for extension but closed for modification. Meaning, you should be able to add new functionality to a module without altering its existing source code. This is usually achieved through abstraction interfaces or abstract classes and polymorphism. Example described. Imagine a shape interface with a calculate area, method, and concrete implementations like circle or rectangle. If you need to add a triangle shape, you create a new triangle class that implements shape and calculate area. You don't need to modify the existing shape interface or the circle and rectangle classes. Any function that previously worked with the shape interface will automatically work with the new triangle without change. Impact on clean code. Promotes stability and prevents ripple effect bugs. When you modify existing code, you risk breaking something. If you can extend rather than modify, your old, tested code remains untouched, reducing uncertainty and increasing confidence. 3. Liskov substitution principle, LSB. Subtypes must be substitutable for their base types without altering the correctness of the program. Meaning, if a class B is a subtype of class A, then you should be able to use an object of type B anywhere an object of type A is expected, and the program should still behave correctly. This often means that methods in subclasses should not violate the expectations set by their parent classes. Example described. If you have a bird class with a fly method and then create a penguin subclass, the penguin should either override fly to do nothing or throw an exception indicating it cannot fly, or preferably the bird class should not have a fly method at all, perhaps only a walk method and a flying bird interface with fly should be introduced for birds that do fly. Impact on clean code. Ensures that inheritance hierarchies are correctly designed and that polymorphism works as expected, leading to predictable behavior and clean, robust abstractions. Violations of LSB often indicate faulty inheritance hierarchies. 4. Interface segregation principle, ISB. Clients should not be forced to depend on interfaces they do not use. Meaning, instead of having one large monolithic interface, it is better to have many small, client-specific interfaces. Example described. Imagine an iRobot interface with methods for move, cook, clean, and fight, a battle robot. If you have a cleaning robot that only needs move and clean, it shouldn't be forced to implement cook and fight, methods that it doesn't need or use. Instead, create smaller interfaces like iMovable, iCooking robot, iCleaning robot, and iFighting robot. A cleaning robot would only implement iMovable and iCleaning robot. Impact on clean code. Reduces the amount of code a client needs to know about less coupling, makes systems more flexible by allowing for specialized implementations, and prevents fat interfaces that are difficult to implement and maintain. 5. Dependency inversion principle, DIP. High-level modules should not depend on low-level modules. Both should depend on abstractions. Abstractions should not depend on details. Details should depend on abstractions. Meaning, this is a crucial principle for achieving loose coupling. Instead of making your high-level business logic directly depend on concrete implementations of low-level details, like specific database drivers or file systems, both should depend on abstract interfaces. Example described. A order service high-level module needs to store order data. Instead of order service directly creating and using a MySQL order repository, low-level detail, order service should depend on an iOrder repository interface, abstraction. The MySQL order repository class then implements this iOrder repository interface. The specific MySQL order repository is injected into the order service at runtime, as mentioned in Chapter 5 regarding low coupling. Impact on clean code. Promotes loose coupling, making systems highly testable. You can inject a mock repository for testing. Flexible, you can easily swap out database implementations without changing the business logic, and maintainable. It's the cornerstone of many modern architectural patterns. Other important design principles. Beyond solid, several other principles complement clean code practices. Don't repeat yourself dry. Principle: every piece of knowledge must have a single, unambiguous, authoritative representation within a system. When you encounter the same logic or data structure in multiple places, it's a violation of dry. Impact on clean code. Reduces redundancy, making code easier to maintain, change it in one place, and it's changed everywhere and less prone to inconsistencies. Identify common patterns and encapsulate them in a single function, class, or module. Keep it simple, stupid kiss. Principle: most systems work best if they are kept simple rather than made complex. Resist the urge to over-engineer or add complexity that isn't immediately necessary. Impact on clean code. Focuses on straightforward solutions. Simple code is almost always easier to understand, test, and maintain than complex code. Start with the simplest solution that works, and only add complexity when driven by concrete requirements. You aren't gonna need it, YHNI. Principle, do not add functionality until you actually need it. This is a direct complement to KISS and Agile methodologies. Impact on clean code. Prevents premature optimization and speculative future-proofing, which often lead to complex and unused code. Focus on solving the current problem and evolve the design as requirements emerge. Principle of least astonishment, POLA. Principle, a component should behave in a way that most users will expect. Its behavior should be consistent and intuitive, avoiding surprises. Impact on clean code. Promotes usability and predictability, making code easier to understand and use correctly. If a function is named delete user, it should delete the user and not also send a notification or update a separate audit log unless that is explicitly part of its documented behavior. The importance of evolution and balancing principles. No single principle is an absolute law. Software design is not about rigidly applying every rule all the time. It's about making informed trade-offs. Sometimes, adhering strictly to one principle might slightly compromise another. The key is to understand the implications of each principle and to seek a balance that best suits the context of your project. Clean code design is an iterative process. You don't necessarily get it perfect on the first try. As your understanding of the problem space grows and your code evolves, you'll continuously apply these principles through refactoring, which we'll discuss in Chapter 10, to improve the system's design. These principles provide a common language and a toolkit for evaluating and improving your designs. Summary key takeaways. Design principles move beyond the basic mechanics of code, guiding the structure and relationships between components. The solid principles SRP, OCP, LSB, ISB, DIP are foundational for creating flexible, maintainable, and extensible object-oriented designs. Dry, don't repeat yourself, reduces redundancy and improves maintainability. KISS, keep it simple, stupid, and YAGNI, you aren't gonna need it. Promote simplicity and focus on immediate needs, fighting against over-engineering. POLA, principle of least astonishment, ensures intuitive and predictable behavior. Software design is about thoughtful trade-offs and continuous evolution. Apply these principles iteratively to improve your system as it grows. Armed with these design principles, you have a powerful framework for building clean, resilient software. While clean code often leads to efficient solutions, it's important to specifically address the relationship between cleanliness and performance, which is exactly what we'll explore in the next chapter. Chapter 9, The Efficient Path, Clean Code and Performance. When developers hear the word efficiency, they often immediately think of speed. How fast does this code run? How quickly does this algorithm process data? And it's true, performance, the speed and resource usage of your software, is a critical aspect for many applications. However, the relationship between clean code and performance is often misunderstood, leading to premature optimization and overly complex solutions. The common misconception is that clean code is inherently slower code, or that achieving performance necessarily means sacrificing readability and maintainability. This chapter will argue that, for the vast majority of cases, clean code enables true, sustainable efficiency, and that the biggest performance bottlenecks are very rarely found in the neatness of your variable names or the smallness of your functions. Efficiency beyond raw speed. Efficiency is not just about raw execution speed. It's about optimizing for the right things, developer efficiency. How quickly can developers understand, modify, and extend the code? This is where clean code shines, as discussed throughout this book. If code takes days to debug or weeks to implement a simple feature, that's incredibly inefficient from a business perspective. Resource efficiency. How much CPU, memory, disk I/O, or network bandwidth does the software consume? This is the traditional definition of performance. Time to market. How quickly can new features or bug fixes be delivered to users? Clean code directly contributes to this. Cost efficiency. What is the total cost of ownership over the software's lifetime, including development, maintenance, and infrastructure? Dirty code often costs more in the long run. Often, developer efficiency and time to market are far more critical to business success than shaving a few milliseconds off a non-critical operation. The problem with premature optimization. One of the most famous quotes in computer science comes from Donald Knuth. Premature optimization is the root of all evil. What is premature optimization? It's the act of optimizing code for performance before you know where the actual bottlenecks are. It's about spending significant time and effort making a non-critical part of the system run faster, often at the expense of readability, maintainability, and sometimes even correctness. Why is it harmful? Increased complexity. Optimized code is almost always more complex and harder to understand. This makes it more prone to bugs and more difficult to maintain. Wasted effort. You might spend hours optimizing a piece of code that only accounts for 1% of the application's total execution time. The gains are negligible. Introduced bugs. Complex, highly optimized code is harder to test and debug, often leading to subtle errors. Obscured logic. The core business logic can become hidden beneath layers of performance-oriented gymnastics, making future development treacherous. The relationship. Clean code enables efficiency. Clean code practices lay the groundwork for true, sustainable efficiency. Readability enables profiling. When you need to optimize for performance, the first step is always to measure. You use tools called profilers to identify the exact parts of your code that are consuming the most time or resources, the bottlenecks. If your code is a convoluted mess of spaghetti, understanding the profiler's output and pinpointing the problematic areas becomes incredibly difficult. Clean, readable code means you can quickly understand what the profiler is telling you and where to focus your optimization efforts. Modularity and clear responsibilities, SRP. When specific functionalities are encapsulated in small, single responsibility functions and classes, it becomes much easier to identify slow components. A profiler will point to a specific function or module. If that function is small and focused, you know exactly what to optimize. If it's a God object doing 20 things, it's hard to tell where the slowness originates. Isolate and optimize. You can optimize a slow component without affecting unrelated parts of the system. This allows for targeted improvements, minimizing risk. Replace inefficient parts. In extreme cases, if a component is inherently slow, its clear interface, due to proper design principles, makes it easier to replace with a more efficient algorithm or data structure without rewriting large portions of the surrounding code. Testability, unit tests. As discussed in Chapter 7, robust unit tests provide a safety net. When you embark on performance optimizations, you often make significant changes to the code's internal implementation. Without tests, you risk introducing regressions. Good tests ensure that your optimized code still produces correct results. You can optimize aggressively, knowing your tests will alert you to any functional breaks. Simplicity and clarity. Complex code often hides inefficiencies. Simple code, where its purpose is clear, makes it easier to spot redundant operations, inefficient loops, or unnecessary memory allocations. Sometimes, the most efficient solution is simply the most straightforward one, once unnecessary complexity is removed. When and how to optimize. The recommended approach to performance optimization is a disciplined one. Build it clean, make it work. Focus on writing clean, readable, correct code first. Prioritize understandability and maintainability over speculative performance gains. Measure, don't guess. Once the system is functionally complete and correctly implemented, if there are perceived performance problems, or if certain performance targets are not met, measure the application's performance using profiling tools. This will show you where the real bottlenecks are. Often, it's I/O operations, network calls, or database queries, not CPU-bound algorithm issues in your primary code. Optimize the bottlenecks. Focus your efforts exclusively on the identified bottlenecks. Applying the 80-20 rule, the Pareto principle, 80% of your performance problems often come from 20% of your code. Choose the right algorithm data structure. Often, the biggest performance gains come from choosing a more efficient algorithm or data structure for the specific problem, e.g., using a hash map instead of an array for lookups. Reduce I/O operations. Minimize database calls, disk reads writes, or network requests. Batching operations or caching data can be very effective. Parallelize distribute. For truly CPU-bound problems, consider parallelizing tasks or distributing the workload across multiple machines. Careful micro-optimizations. Only after exploring the macro-level optimizations, algorithm, I/O should you delve into micro-optimizations, e.g., tweaking loops, bit manipulation, as these often yield minimal gains for significant complexity. Repeat and verify. After each optimization, remeasure to ensure the change had the desired effect and didn't introduce new bottlenecks. Crucially, run your unit and integration tests to ensure correctness. Common pitfalls and solutions relevant to clean code. N+1 query problem. A common database performance issue where you fetch n parent records, and then for each parent, you execute an additional query to fetch its child records. Clean code application. While not strictly a code cleanliness issue, a clean architecture, e.g., using a dedicated data access layer or repository pattern, makes it easier to identify and refactor these patterns into single, batched queries. Excessive logging. While logging is crucial for error management, Chapter 6, overly verbose logging, especially in production, can introduce I/O overhead. Clean code application. Use appropriate logging levels and configure them carefully for different environments. Ensure detailed logs are only enabled for debugging or specific environments. Unnecessary object creation. In some performance-critical loops, repeatedly creating and destroying objects can lead to garbage collection overhead. Clean code application. If profiling reveals this to be a bottleneck, consider object pooling or reusing objects, but only if a tangible performance gain is measured. Don't sacrifice clarity upfront for speculative gains. Summary key takeaways. Efficiency encompasses more than just raw speed. It includes developer efficiency, time to market, and overall cost of ownership. Avoid premature optimization. It leads to complex, buggy, and often wasted effort. Clean code is not anti-performance. It enables performance. Readability, modularity, and testability make it easier to identify, isolate, and effectively optimize true bottlenecks. Measure, don't guess. Use profilers to find where your application is actually spending its time before attempting any optimizations. Focus on the biggest bottlenecks first. Often, improvements come from choosing better algorithms, optimizing I/O, or reducing network communication, not from micro-optimizations in simple code. Always verify correctness. After any optimization, run your tests to ensure no functional regressions were introduced. By prioritizing clean code first, you build a system that is easy to understand, evolve, and, when necessary, efficiently tune for performance. This disciplined approach ensures that your software is not only fast, but also sustainable. Our next chapter will dive into the continuous process of keeping your code clean and improving its design, refactoring. Chapter 10. The continuous polish, the art of refactoring. Building software is not like constructing a building that, once finished, remains static. Software is more akin to a garden. It grows, it evolves, and it requires constant tending. If left untended, entropy sets in, weeds take over, and what was once beautiful and productive becomes overgrown and unmanageable. Refactoring is the dedicated, disciplined act of tending your software garden. Refactoring is the process of restructuring existing computer code, changing its internal structure without changing its external behavior. It's about improving the design of your software after it has been written, making it easier to understand, cheaper to modify, and ultimately more stable. If writing clean code is about applying good design principles from the start, refactoring is about continuously improving the design of code already written. Why refactor? The primary reasons for refactoring are: improve code design. Even with the best intentions, initial designs might not perfectly anticipate future needs or edge cases. Refactoring addresses this organic evolution, adapting the code structure to better fit its current understanding and future direction. Make software easier to understand. By clarifying intent, simplifying complex logic, and eliminating redundancy, refactoring vastly increases the readability and comprehensibility of code. Reduce technical debt. As we discussed in Chapter 1, dirty code is technical debt. Refactoring actively pays down this debt, preventing it from spiraling out of control. It's an investment in future productivity. Find bugs. The act of refactoring often forces you to look at code from a new perspective, making hidden assumptions or logical flaws evident. This can help you discover bugs that might otherwise remain hidden. Increase development speed. Paradoxically, regular refactoring, while taking time in the short term, significantly increases long-term development velocity. Clean, well-structured code is faster to work with. When to refactor. The Boy Scout rule in action. The Boy Scout rule, leave the campground cleaner than you found it, is the golden rule for refactoring. It suggests that every time you touch a piece of code, you should leave it a little bit better than you found it. Opportunistic refactoring. This is the most common form. As you add a new feature or fix a bug, you inevitably interact with existing code. If you find a function that's too long, a class with too many responsibilities, or a poorly named variable, take a few minutes to improve it before you add your new code. Small, continuous improvements prevent the buildup of technical debt. Planned refactoring, dedicated sprints time. Sometimes, the accumulated debt is too great, or a significant architectural change is needed. In these cases, dedicated time or refactoring sprints might be necessary. This should be a conscious decision, often driven by the inability to efficiently add new features or unmanageable bug rates. Before adding a feature. If the existing code structure makes it hard to add a new feature, refactor it first to make the addition easier and cleaner. When fixing a bug, often, the root cause of a bug is not just a simple mistake, but a design flaw or overly complex code. Refactor the problematic area to prevent similar bugs in the future. During code reviews are excellent opportunities to identify areas for refactoring. Insights from fresh eyes can pinpoint confusing logic or poor design. Crucial prerequisite: a robust test suite. You absolutely, positively cannot refactor effectively without a comprehensive suite of automated tests. As discussed in Chapter 7, tests are your safety net. Refactoring involves changing the internal structure of code without changing its external behavior. Only automated tests can confirm this. Before you refactor, ensure you have tests that cover the code you intend to change. If not, write them first. Run your tests frequently as you refactor, ideally after every small, atomic change. This immediate feedback loop is critical. If a test fails, you know exactly which recent change caused it. Without tests, refactoring becomes risky, opening the door to introducing subtle bugs that could go unnoticed until production. Common refactoring techniques described. Refactoring often involves applying common patterns and techniques. Here are some fundamental ones. Extract method function, revisited from Chapter 3. Problem: a long function with multiple responsibilities or complex blocks of code. Solution: identify a logical block of code within the function that performs a single, coherent task. Move that block into a new, smaller function and give it a descriptive name. Replace the original block with a call to the new function. Benefits: improves readability, reduces function size, can lead to reusability, simplifies testing. Rename variable function class. Problem: poorly named elements that don't reveal their intent, Chapter 2. Solution: use your IDE's refactoring tools to safely rename elements throughout your codebase. Benefits: vastly improves readability and self-documentation. Extract class. Problem: a class that has grown too large, is doing too many things, or has more than one reason to change, violates SRP for classes, Chapter 5. Solution: identify a cohesive group of related variables and methods that represent a distinct concept. Move them into a new, separate class. Example described. A user class that handles both user details and user authentication logic. Extract the authentication logic into a new user authenticator class. Benefits: improves cohesion, reduces class size and complexity, makes classes easier to manage and test. Inline variable method. Problem: Sometimes, a temporary variable or a delegated method adds unnecessary indirection or complexity, especially if its name isn't much clearer than the expression it holds. Solution: replace the variable with its actual value or replace the method call with the body of the method itself. Benefits: can simplify code that has become overly fragmented. Use cautiously. Over-inlining can make code less readable. Move method field. Problem: a method or a data field is in the wrong class. It makes more sense to be with another class that uses or manipulates it more frequently. Solution: move the method or field to the more appropriate class. Benefits: improves cohesion and reduces coupling between classes. Replace conditional with polymorphism. Problem: long conditional statements, if-else, or switch case, that alter behavior based on the type or state of an object. This often violates the open-closed principle, Chapter 8. Solution: use inheritance and polymorphism to handle different behaviors. Define an interface or abstract class, and then create specific subclasses for each variation, moving the specific behavior into the respective subclass. Example described. Instead of if employee type equals salaried, calculate salary for salaried. Else if employee type equals hourly, calculate salary for hourly. Create salaried employee and hourly employee subclasses, each with its own calculate salary method. Benefits: makes code more extensible, add new types without modifying existing code, reduces complexity, and adheres to OCP. The refactoring workflow. A typical refactoring cycle looks like this. Identify a code smell, recognize an area that needs improvement, e.g., a function that's too long, a redundant piece of logic. Write or ensure tests. Verify that you have automated tests covering the area you're about to refactor. If not, write them. Choose a small refactoring. Select one specific atomic refactoring technique, like extract method. Perform the refactoring. Use your IDE's automated refactoring tools where possible, or make the change manually. Run all tests. Immediately run your entire test suite to ensure no regressions were introduced. Commit your changes. Once tests pass, commit the small atomic refactoring. Each refactoring step should be a separate, tested commit. This makes it easy to revert if something goes wrong. Repeat. Continue identifying smells and applying refactorings. This small step approach, coupled with immediate feedback from tests, makes refactoring a low-risk, high-reward activity. The dangers of Big Bang refactoring. Avoid Big Bang refactorings, attempting to rewrite or restructure huge parts of the system all at once without continuous testing. These often lead to long and complex branches, making it difficult to integrate changes with the main codebase. Increased risk, a higher chance of introducing numerous bugs. Demotivation. Long, arduous refactoring efforts without visible progress can demoralize a team. Scope creep. Over time, refactoring can morph into a full rewrite rather than a targeted improvement. Summary key takeaways. Refactoring is the act of improving code's internal structure without changing its external behavior. It's essential for maintaining software quality over time. It reduces technical debt, makes code easier to understand and modify, and ultimately increases development speed. A robust suite of automated tests is an absolute prerequisite for safe and effective refactoring. No tests, no refactor. Adopt the Boy Scout rule and do small, opportunistic refactorings whenever you touch code. Utilize common refactoring techniques like extract method, rename, extract class, and replace conditional with polymorphism. Follow a disciplined workflow. Identify smell, test, refactor in small steps, run tests, commit, and repeat. Avoid Big Bang refactorings. Favor continuous, incremental improvement. Refactoring is a critical skill for any developer committed to craftsmanship. It's the ongoing process of polishing your code, ensuring it remains clean, adaptable, and efficient. But software is rarely built in isolation. Our final chapters will explore how clean code practices translate into working effectively within teams and how to cultivate a continuous journey of improvement. Chapter 11. Collaborative Craftsmanship. Clean Code and Teams. Up to this point, our discussion has largely focused on the individual developer's responsibility in writing clean code. We've explored naming, functions, classes, error handling, testing, design principles, performance, and refactoring, all practices that elevate one's personal coding craftsmanship. However, in today's software development landscape, very few products are built by a single individual. Software is overwhelmingly a collaborative endeavor, often involving diverse teams working on the same codebase. In a team environment, clean code transcends personal preference. It becomes a critical enabler of communication, efficiency, and shared understanding. When multiple developers are contributing, merging, and reviewing code, the clarity and maintainability of that code directly impact the team's ability to deliver high-quality software consistently. Chaos quickly ensues if every developer writes code according to their own subjective, clean standards, or worse, without any standards at all. The team as an organism. Shared understanding. Imagine a team of surgeons operating on the same patient. If each surgeon used different, undocumented instruments, had unique ways of performing incisions, and communicated vaguely, the outcome would be dire. They need shared protocols, standardized tools, and clear communication to work effectively. Your codebase is effectively a shared brain for your team. Every line of code written by one developer will, at some point, likely be read, debugged, and modified by another. Clean code facilitates this interaction by reducing onboarding time. New team members can quickly understand existing code, contributing meaningfully sooner, rather than spending weeks deciphering arcane logic. Minimizing misunderstandings. Clear, self-documenting code reduces ambiguity, leading to fewer misinterpretations during development and fewer bugs. Enhancing communication. Good code acts as a common language. Discussions can focus on high-level design and business logic rather than low-level syntax and obscure patterns. Promoting predictability. A consistent style and adherence to common principles make the codebase predictable, which builds confidence and reduces cognitive load during development. Establishing shared clean code principles. Creating a culture of clean code in a team requires conscious effort and agreement. It's not about imposing dictatorial rules, but about fostering a shared understanding and commitment to quality. Acknowledge the value. The whole team must genuinely understand and agree on why clean code matters. If some team members see it as academic overhead and others as fundamental, friction will arise. Discuss the benefits: developer productivity, fewer bugs, reduced technical debt, and the costs of dirty code. Define shared standards, coding conventions. Agree on stylistic elements, indentation, brace placement, naming conventions, e.g., camel case for variables, Pascal case for classes, line length, etc. Automated formatters, like Prettier, Black, or Go FMT, can enforce many of these without human intervention. Architectural guidelines. Define how subsystems communicate, what patterns to use for common problems, and how to structure layers, e.g., where business logic goes V's. Data access. Error handling policies. Standardize how errors are caught, logged, and communicated across modules and to users. Testing strategy. Agree on the types of tests to write, their coverage targets, and how they should be structured. Document guidelines briefly. Don't write a 100-page manual. Keep guidelines concise, actionable, and easily accessible, e.g., in your team's wiki or a simple GitHub readme. Focus on why certain standards exist. Lead by example. Senior developers and team leads must embody clean code practices. Their code should demonstrate the agreed-upon standards, and they should champion the continuous pursuit of quality. Code reviews. The crucible of cleanliness. Code reviews are perhaps the most powerful mechanism for fostering and maintaining clean code standards in a team. They are a collaborative process where other developers examine code for defects, improvements, and adherence to established guidelines. Benefits of effective code reviews. Quality assurance. Catch bugs, logical errors, and design flaws early. Knowledge sharing. Disseminate knowledge about the codebase, features, and design patterns. More eyes on the code means more people understand it. Mentorship and learning. Junior developers learn from experienced peers, and even senior developers can gain new perspectives. Consistency enforcement. Ensure adherence to agreed-upon clean code standards, naming conventions, and design principles. Shared ownership. When multiple people review a piece of code, there's a shared sense of responsibility for its quality. Tips for effective reviews: be constructive, not critical. Frame feedback as suggestions for improvement, not finger-pointing. Focus on the code, not the person. Consider extracting this method for better readability is better than this method is too long. Review small chunks. Large code changes are intimidating and hard to review thoroughly. Encourage developers to submit smaller, focused pull requests. Automate where possible. Use linters, formatters, and static code analysis tools to catch mundane syntax issues or formatting violations. This frees up human reviewers to focus on design, logic, and architectural concerns. Focus on principles. Go beyond surface-level naming, Chapter 2, and function size, Chapter 3. Discuss the single responsibility principle, Chapter 5, open-closed principle, Chapter 8, and the appropriate use of exceptions, Chapter 6. Educate, don't dictate. If a guideline is violated, explain why it's a problem and what the preferred approach achieves. This function violates SRP because it has two distinct reasons to change. If the logging mechanism changes, this function and the processing logic would both need modification. Make it a habit. Integrate code reviews into your regular development workflow. Approve and merge quickly. Don't let pull requests sit for days. Prompt reviews reduce context-switching costs and bottlenecks. Pair programming, real-time cleanliness. Pair programming, where two developers work at one workstation on a single piece of code, offers an intense, real-time approach to clean code. How it works: one developer, the driver, writes code, while the other, the navigator, observes, reviews each line as it's typed, and thinks about strategic direction and potential pitfalls. Roles are swapped frequently. Benefits for clean code: instant code review. Errors and design flaws are caught immediately, often before a single line of bad code is committed. Shared knowledge transfer. Knowledge is constantly transferred between team members. Increased quality. Two minds are better than one, leading to more robust and thoughtful solutions. Built-in consistency. As both developers contribute to the code, it naturally adheres to a common style and understanding. Improved design. Discussing design decisions as they happen often leads to better application of principles like solid. While it might seem slower upfront, pair programming often leads to higher quality code, fewer bugs, and greater overall productivity due to less rework and debugging later on. Empowering continuous improvement. Clean code in a team is not a one-time achievement. It's a continuous journey. Dedicated refactoring time. Encourage and allocate time for developers to continuously refactor and pay down technical debt. Integrate it into sprint planning. Fix the broken window. If you see a piece of dirty code, fix it. Leaving broken windows, small pieces of bad design or code, encourages further neglect, while fixing them sets a positive example. Postmortems and retrospectives. Regularly discuss what went well and what could be improved in your development process. This includes candid conversations about code quality and its impact on your team's efficiency and morale. Invest in tools. Utilize IDEs with strong refactoring capabilities, code formatting tools, static analysis linters, and robust version control systems. Automate as much of the cleanliness checking as possible. Summary key takeaways. Clean code is a team sport. It's essential for efficient communication, shared understanding, and productivity in collaborative development environments. Establish shared principles and guidelines. Define and agree upon coding conventions, architectural standards, error handling, and testing strategies. Document them concisely. Code reviews are vital. They ensure quality, foster knowledge sharing, reinforce consistency, and provide opportunities for mentorship. Be constructive, review small chunks, and automate stylistic checks. Consider pair programming for real-time quality assurance, knowledge transfer, and shared design decisions. Empower continuous improvement. Allocate time for refactoring, fix broken windows, learn from retrospectives, and invest in automation tools. Fostering a culture of collaborative craftsmanship centered around clean code transforms a group of individual coders into a high-performing software development team. It builds trust, minimizes friction, and ultimately leads to more sustainable and successful projects. This leads us to our final discussion: The Unending Journey of Mastering Your Craft. Chapter 12, The Unending Journey. Mastering Your Craft. We've covered a significant landscape in this journey towards clean code. From the foundational importance of meaningful names and focused functions to the elegance of clean classes, robust error handling, the safety net of testing, the architectural guidance of design principles, the strategic pursuit of efficiency, and the continuous art of refactoring. We also explored how these individual practices coalesce into a powerful force for collaborative teams. But here's the most crucial truth. Mastering clean code is not a destination. It is an unending journey. Software development is not a static field. New languages, frameworks, tools, and paradigms emerge constantly. The problems we solve evolve, and so too must our skills and understanding. Clean code, at its heart, is a philosophy of continuous improvement, a commitment to craftsmanship, and a professional responsibility. The professional developer, beyond just getting it to work. The difference between a coder and a professional developer often lies in this distinction. A coder might aim to simply make it work. A professional developer, however, aims to make it work well. They care not just about the immediate functionality, but also about maintainability. How easy will it be for someone, including my future self, to understand and change this code in 6 months, a year, 5 years? Testability. How can I verify that this code does what it's supposed to do reliably and consistently? Readability. Can another human being easily follow the logic and intent of my code without extensive mental effort? Resilience. How well does this code handle unexpected situations, errors, and changes in its environment? Sustainability. Can this code evolve and adapt gracefully over time as requirements inevitably shift? These are the hallmarks of clean code and the attributes of a true craftsmanship mindset. Never stop learning, never stop practicing. Just like any craft, carpentry, music, writing, or medicine, expertise in software development is honed through deliberate practice and continuous learning. Read. Immerse yourself in the wisdom of others. Beyond this book, explore other foundational texts on software craftsmanship, design patterns, and programming paradigms. Engage with articles, blogs, and research papers from thought leaders in the field. Write code every day. The best way to improve your coding skills is to code. Work on side projects, contribute to open source, or simply tackle small coding challenges. The muscle memory and intuition you build through consistent practice are invaluable. Practice deliberately. Don't just write code, write with intention. Pick one clean code principle each week and focus consciously on applying it in your daily work. For example, for 1 week, focus solely on writing the most meaningful names you possibly can. The next, strive to make every function as small and single-responsible as possible. Learn from others, code reviews. Actively participate in code reviews, both as a reviewer and as the author. Offer constructive criticism and, more importantly, be open to receiving it. See it as an opportunity to learn and improve. Pair programming. As discussed in Chapter 11, pair programming is an incredible learning tool. The constant feedback and shared problem-solving accelerates skill development. Mentorship. Seek out mentors whose code you admire. Be willing to mentor others as you grow. Teaching often solidifies your own understanding. Reflect and introspect. Regularly take time to review your own code. Ask yourself, could this be clearer? Is this the simplest solution? How would I approach this if I had to do it again? What could I have done better? Learn from your mistakes and successes. The courage of cleanliness. Writing clean code requires courage. Courage to say no. To rushed deadlines that demand shortcuts over quality. To features that add unnecessary complexity without thoughtful design. Courage to take an extra step. To refactor a suboptimal piece of code even when it works. To write comprehensive tests when the pressure is on to just ship. Courage to admit mistakes. To acknowledge areas where your code or design could be improved, and to dedicate the effort to make it so. Courage to be the change, to champion clean code practices within your team, even when others might resist. To lead by example and demonstrate the long-term benefits. The unseen value of clean code. The value of clean code often remains unseen. When a system is working smoothly, adapting easily to changes, and rarely producing bugs, its quality is almost invisible. It's when code is dirty that its impact becomes painfully apparent through missed deadlines, frustrated developers, and system failures. Just as a well-maintained bridge goes unnoticed until it fails, the beauty of clean code is in its quiet reliability. Your commitment to clean code is an investment in your career, your team's success, and the robustness of the software you build. It's a craft that rewards dedication with clarity, confidence, and control. It transforms the often challenging act of software development into a more joyful, productive, and sustainable endeavor. So, continue to seek simplicity. Strive for clarity, embrace consistency, validate relentlessly, and remember that every line of code you write is a statement about your commitment to your craft. The journey is unending, but the rewards are profound. Keep polishing, keep learning, keep building clean.